Welcome to the fourth lecture video in our Class 4 time series of lecture videos. I know you've been waiting in suspense to see what reason lies behind the fact that our trines rotate in a disrotatory sense under thermal conditions and a conrotatory sense under photochemical conditions. Well, our trine starts out in thermal conditions to be in the ground state. What does that mean? That means all of its electrons are in the lowest energy molecular orbitals for the trine pi system. And what do I mean there? Well, in our trine, we have a total of 6 p orbitals, right? And if we have 6 p orbitals, well, we will have 6 molecular orbitals associated with those. You can see the first 3 molecular orbitals are drawn here. And our lowest energy molecular orbital for our trine, with the methyl groups both pointing out, have p orbitals whose lobes have all the same phase on the same side of the plane of the trine. If we step up one level in energy, we add one node, and we do so equitably, so we cut across a carbon-carbon bond such that we have 3 p orbitals on one side and 3 p orbitals on the other. And when we go across that node, the phases of the lobes change. So on the left side of our trine, all the lobes on the top side of the plane have this light phasing, whereas on the right side of the trine, in the second molecular orbital, all the p orbital lobes on the top side of the plane formed by the trine now have a dark phasing. And what that means is, yeah, you can't overlap that dark phase lobe with this light phase lobe on the same side of the plane, on the top side of the plane of that trine. We step up one more level in energy, and lo and behold, we have 2 nodes now, and it kind of looks like we have isolated pi bonds, right? Ultimately, at any rate, for our trine in this ground state, we are reacting from this very most highest occupied molecular orbital, this pi 3. And if we are doing that in order to form a carbon-carbon single bond and ultimately a cyclohexadiene product, in order to do that between these two ends, we have to bring this light phase lobe into the plane such that it's horizontal in order to have it overlap with this light phase lobe. And so we turn this propeller on the left side in a clockwise manner, and if we're doing that, we have to turn this other propeller on the right side in a counterclockwise manner. And that effect, once those 2 light phase lobes end up horizontal, our reaction has stopped. We've formed a carbon-carbon single bond, and both methyl groups stop pointing up, and they're on the same side of the plane of that cyclohexadiene that is formed. Similarly, I could have brought these 2 dark phase lobes together, in which case I would be turning the left propeller in a counterclockwise sense, but then the right propeller would have to be turned in a clockwise sense. And in that case, both methyl groups would end up pointing down on that cyclohexadiene product that is formed, but that would be exactly the same product. Now, if I hit my trine with light, H nu, that can actually be absorbed by an electron, say in the highest occupied molecular orbital, and I can promote it to an excited state. What does that mean? That means I could promote that one electron to pi 4, right? The next higher molecular orbital in energy. And that particular molecular orbital has 3 nodes, 3 of these vertical nodes. And what that means is, if I were to do the same sort of reaction from pi 4 now, in terms of forming my cyclohexadiene product, what I would be doing is, if I were turning this leftmost propeller in such a way to bring that light phase lobe in a horizontal, in the plane, to overlap with this light phase lobe, if I'm turning this in a clockwise sense, well then I have to turn the propeller on the right also in a clockwise sense. So that's conrotatory, right? In order to get that light phase lobe horizontal and overlapping with this light phase lobe and forming a carbon-carbon single bond. Well, what effect does that have on the methyl groups? This leftmost propeller turns in such a manner such that the methyl group stops pointing up. This rightmost propeller turns until that light phase lobe is horizontal and overlapping with this one, but then the methyl group stops pointing down. Now, I could have gone both in a clockwise sense, but then I could have also turned these propellers in such a way to bring the dark phase lobes to overlap. If I were doing that, both propellers would have to go counterclockwise, and I would simply get the enantiomer, right? This methyl group would be pointing down, and this methyl group would be pointing up. So this is the reason why, under thermal conditions, our triene does a ring closing reaction in a disrotatory sense, so our propellers are turning in opposite directions, whereas under photochemical conditions, so H nu, we're now reacting from pi4, and our propellers are turning in a conrotatory, that is, in a similar sense to each other. Of course, our triene has a couple other molecular orbitals, right? Pi5 and pi6. You just keep adding nodes until you get to the highest energy molecular orbital, but they don't really come into play in these electrocyclic reactions for the triene. We're mainly concerned with pi3 and pi4. So hopefully you understand now that as a reason for the way our trienes react. We'll look at how a different type of electrocyclic reaction substrate works. Our triene is kind of an interesting case. There are 6 pi electrons. That's characteristic of a 4n plus 2 electron system, where n is an integer. Could be 0, 1, 2, or 3, so on and so forth, right? There's another sense that is 4n systems, and like I said, we'll look at that in the next video. I'll see you then.